Lesson is going to focus on how we can use logarithms to help us solve exponential growth and decay problems. So as a quick review, our exponential function for growth and decay is in this format: y equals a times b to the power of x, where a represents your initial amount of substance or population or whatever variable it is you happen to be dealing with. A represents your initial amount at time 0. So when x is 0, your function is equal to b to the power of 0 is 1. Anything to the power of 0 is 1. Your function is y equals a. So a represents your initial amount at time 0, which represented using an ordered pair would be 0, a. And again, this would also be when your x value is equivalent to 0 in this case, you've also identified your y-intercept. So b represents your growth or decay rate. It represents growth if your b value is greater than 1, and it represents decay if b is less than 1. So let's take an example. Let's say we have a population of bacteria that's growing. And let's say we are starting with 2,354 bacteria. And it grows at a rate of 6% per hour. So the first thing we want to do is put this into the proper form. So at time 0, our bacteria population is 2,354. So we know that that's going to be our A value because that's our initial amount at time 0. So y equals 2,354. Now we have some growth rate here, and to the power of t. Notice I went ahead and replaced that x with a t because t represents time. So there's a 6% growth rate. But I need to be cognizant of the fact that I can't just plug in a 0.06 there. Because what's going to happen when I multiply 2,354, and we'll say t is 1 in this instance, times 0.06, is I'm going to get 6% of the population. But what I really want to know is what's my current population, which would be 2,354 plus that 6%. So I need to add in 1 plus my growth rate to account for that original amount as we calculate. So, and if you look at order of operations, so assuming t is 1, so we'll put a 1 there. So raised to the power of 1. If we look at our distributive property, 2,354 times 1 plus 2,354 times 0.06. So again, this is going to give us how many bacteria are present after 1 year. So it's going to take my original amount plus my 6% of growth. And that will give us the number of bacteria that we would expect after 1 year. So that's why we make sure we add that 1 plus your growth rate. Okay, so if the question is asking, how long until the bacteria population doubles? Okay, so how long until it doubles? So how long until we have 2 times our original population? So how long until we have 4,708 bacteria? So we're going to set up our new equation. We want to know how long it takes until we have this amount. That's equivalent to A, 2,354, times, and I am running out of space here, so times 1.06 to the power of t. So our goal is to solve that function for t. So let me give us a little bit more space here. So we are going to use our properties of logarithms to help us solve this. Traditionally, when we solve linear functions, 2x equals 8, it's fairly straightforward. We either divide or multiply to isolate our variable here. But it's a little bit more complicated when our variable is in the exponent position. And that's why logarithms are so awesome. So our log power property, let's review that one real quick. So if we have log base b of m to the power of k, that's equivalent to k times log base b of m. And presumably we've already learned this through an exploration activity. So this property is really cool because it allows us to take that exponent variable and multiply it by our logarithm. Well, when we first look at this, we don't have any logarithms. So how are we going to use this property? Well, with equations, as long as whatever you do to one side, you do to the other side, it's okay. It's fair game. So step one, we want to get t as isolated as we possibly can before we start filling in logarithms. So this 2,354 times 1.06 to the power of t, we can go ahead and divide both sides by that amount so that we just have 1.06 to the power of t on one side. So I'm going to have 4,708 divided by 2,354, and that's going to be equivalent to 1.06 to the power of t. And again, giving us a little bit more space. So we still have our question, how long until it doubles? All right, so we want to go ahead and simplify. What is 4,708 divided by 2,354? And that is 2, which, wow, yeah, I just did that on my calculator. Feel free to judge me. I did everything. Okay, it's 2. It should be 2. We were looking at how long it takes until the population doubles. So 2 equals 1.06 to the power of t. All right, so we want to get this variable out of our exponent position. So we're going to take the log of both sides. Again, whatever you do to one side, as long as you do it to the other side, you still have an equivalent expression. All right, so now we can use our property. So we're going to bring this t down. So that's equivalent to log of 2 is equivalent to t times the log of 1.06. We are so close to solving for t at this point. So now we're going to divide both sides by the log of 1.06. And so we have t is equal to log of 2 divided by log of 1.06. Now I know it's very tempting. You see log over log. Ooh, let's reduce that to 1. You can't do that. This isn't the word log times 2. Log of 2 represents 10 to the power of what will give me 2. So you can't separate these guys. So you need to, at this point, if it's not one that you can solve in your head, then it's time to break out a calculator. And this time we actually need the calculator, unlike my divided by to get 2. So log of 2 is 0.301. And log of 1.06 is equivalent to 0.025. And we're going to divide those two. And that gives us 12.04. So what does that mean, 12.04? Well, remember, we were looking to determine how long until the bacteria population doubles. Well, bacteria population doubles in in 12.04 hours. So in 12.04 hours, the bacteria population